Hello everyone, my name is Robert, and this is Lab2, the magnetic field of a dipole. The purpose of this lab was to measure the distance dependence of the magnetic field due to a bar magnet and compare those measurements to some theoretical computations with the bias of part law. To do this, we used two models. The first was an experiment with a small permanent magnet measured with a magnetometer app, and then we used a computational model in Python to visualize the magnetic field and also compare it to some theoretical values. By the end of the lab, we saw that the magnetic dipole moment of our chosen magnet was 3.85 amps meters squared. For a 45-degree B measurement, we saw that the theoretical was pretty close in one direction, but in the y direction it was nearly double of what it should have been, and that's probably due to some interference or accuracy of measurements. So the fundamental principles for this lab are going to revolve mainly around calculating the magnetic field from the bias of part law, and from this we derive the magnetic field equation for a dipole off-axis, as well as the one on-axis that we'll be using for measurements, and also taking into account the magnetic field of the Earth. For the first part of the experiment, we first had to calibrate the magnetic meter app to the magnetic field of the Earth, which we found in the general location where I am is around 45.40 microteslas. It should have been closer to 48, but there is interference through the Wi-Fi and surrounding metal objects, so that's as close as I could get. The initial conditions for this, the system is going to be the magnetometer observation location, which we determine on the phone in both the X and Y axis to see where it is closest to the sensor. The surroundings is the bar magnet and the magnetic field of the Earth. Once we calibrated the location of the sensor inside the phone, we then went on to the data collection, which we took the readings of the magnetic field at a given distance. So we measured it at 20 centimeters, 70 centimeters, 120 centimeters, 170, and 220, and the corresponding magnetic field at those points. And using the equation that the magnetic field of a bar magnet is equal to K, so a collection of constants, times R to the end, we graph this ln of the magnetic field versus ln of R to find the slope, which is going to give us ln of K as well as N. Setting K R to the N equal to the on-axis magnetic field of a dipole that we already have discussed, we're able to find, for plug in N and K, to find mu, and that's where we get the 3.85 amps per meter squared. To help visualize the magnetic field at given points, we first use the magnetic dipole moment mu from our experiment to plug into our code. That's going to use the dipole off-axis equation to calculate and place arrows around the magnet. So this equation was plugged into our dipole B function, and then use that to help draw the arrows around the magnet. Here we can see the orange and red arrow represents the on-axis, the blue colors represent the perpendicular axis, which the arrows again are drawn here using the dipole B function to help draw the axis of these arrows. The distance for this was arbitrarily set to 0.3. We can see that the on-axis was 2.85 times 10 to the negative 5 Teslas magnetic field, which is not too far off the calculated experimental values we got from our 20 before. To find the 45-degree axis arrow, experimentally, first that we did a d distance to find a distance of which corresponded to around 100 microteslas, and that d distance perpendicular on the hypotenuse would be 0.311 meters, which the total magnitude of that magnetic field was around 1.22 times e to the negative 5. Placing this into the computation model, we see that B at the 45-degree angle given with the purple magenta arrow is to be 6.3 e to the negative 6, 1.9 e to the negative 5, 0. Comparing that to what we found experimentally computationally, the computation was about double-ish about what we should have found in magnitude, but it was relatively close as it's still in the same margin of microteslas. To answer the what-ifs, if measurements were taken without aligning to Earth's magnetic field, then we would need to compensate in the x directions for any measurements. If we had two magnets used, then we would expect the magnetic field to be twice, so it'd be 2 over r to the third, that we should see the scaling of distance instead.